all their, each wire by itself can achieve a disk of translations. And so if you orient those translations perpendicular to the wires and you find what's common between all the wires, the translation-wise, you'll find a translation. That's another way to find like hoops and stuff. Right, okay, but anyway, let's look at constraints in series. Okay, so constraints in series behave differently. Instead of finding what's common between them, or like kind of the intersection, you know, that upside down cup shape kind of thing, it's the intersection, you find what's common between them. That's what you do in parallel with freedom spaces. But when you have things in series, so here's a parallel guide mechanism, and you stack it in series with itself. Here's the ground. I should add thatching. Here's the intermediate stage, and now you stack it in series with itself. The final stage will inherit the degrees of freedom of both, and it will get every combination of the two. So it's not just the sum of, you know, it's not just for this one, if you draw a Venn diagram, it's like two circles overlap. You know, you just show what's overlapped. Well, this, if you have two circles overlapped, you not only take everything in each circle, but you sum them together and get even more than you started with. So here you just started with 2, but now you get an infinite number in a disk. Okay, so you linearly combine. They inherit everything from the 2, and you linearly combine it. Okay, so that's the rule. Constraints in parallel, you find out what's common in their freedom space, and constraints, you know, in series, you take the freedom spaces and you linearly combine. You add them. They inherit everything and then some. Okay, so those are principles to be aware of. Okay, these next two slides are two of the most important for the entire fact theory, because they show you how you deal with freedom and constraint spaces in parallel and series, which is very instructive for designing and analyzing, okay? As you'll see in a minute here. So a lot of this you already know, but I'm just going to re-fortify it in this context. So, and I'm going to do it in the context of this example. Say you just have a parallel system with 2 wires, right? Well, before, what we did is we found all the red lines intersect all these wires, blah, 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 and here's all the red lines intersect all the wires, satisfy the rule of commutative patterns. Then you could find all the blue lines intersect all these, and you'd find this. Okay? Or what you could have just done is taken these blue pure force lines and linearly combined them. You inherit this and this, but just linearly combine them, and you get all this and a moment. Okay, so constraints in parallel, you linearly combine, you add them. Okay? All right, but each of these wires has a freedom space that's essentially a bunch of intersecting red planes, okay, as you see here, and a disk. Let's see, where's my freedom space? Yeah, so check it out. Each wire has intersecting red planes and a disk of translations, then a bunch of screws that we're not going to draw. Okay, but here's the freedom space without the screws of each wire. Okay, you'll find, if you can visualize these intersecting red planes and these 2 disks, and I were to ask you, what is the intersection of both of these? So here's the intersection sign, this upside down cup. You know, it's basically, you find what's common between the 2 of them. Well, you would find the only plane that's common between the 2 is this plane that's highlighted red. Okay, the plane established by the 2 wires. And you would find, though, there are other red lines common to both of these, which is every red line in the box that's parallel to these wires would be common between these 2 spaces, red spaces. That's all that's common with red. And then, of course, these disks point in perpendicular directions. All of them are common to each other. They don't have a location, right? They just have directions. So you might as well just move it to the center here. I mean, you can put it anywhere you want. It doesn't have a location. It's just this is the disk that's perpendicular to these 2 wires. Okay, and you would find, if we took all the screws of this guy and all the screws of this guy and found what's common, all the screws would be these guys that are common. Okay, so we've just oriented this constraint space like there. We've oriented its complementary freedom space like there. Of course, all these guys are on top of each other, and this is on top of it, but that just looks like a mess. So we blow it up. And I drew these how it is on the fact chart here. So right here, right? That's the fact chart. Okay, it doesn't show the pure moment in there because I've gotten rid of pure moments, but there's a pure moment on there. Okay, okay. So 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 hopefully I've convinced you that the constraint space of this is this, and the freedom space of this is this, and the constraint space of a single wire is that, and the freedom space of this is that. So, okay, so again, when you put constraints in parallel, you linearly combine them, and you get that. When you put freedom spaces of constraints in parallel, you find the intersection, what's common between the two of them. Okay, so that's the rule for parallel. You know, whether you realize that or not, when you put constraints in parallel, you can either take their constraint spaces and add them, or you can take their freedom spaces and find what's common, or the intersection of them. Okay? So, but it's the exact opposite in serial land. Okay? So let's now take this serial system. This is, you know, we took this exact same parallel module from the previous slide, this guy, and now we're going to stack this parallel module on top, two blades that intersect up at the stage. So now we have a ground, intermediate body, and a stage. Okay? And if you held the intermediate body grounded and just looked at that parallel module, you would see its stage would rotate with a single freedom space at the intersection of those two blades. Okay, that's how it would move. Okay, so now we know the freedom space of this system is this. We know the freedom space of this system up here stacked on top is this rotation. And so now you ask yourself, well, what's the total freedom space of the stage, right? If you only ground it, you allow the intermediate body to move, and you also allow the stage to move, then what you get is, you know, if you go back, remember it's like this, you stack it in series, you not only inherit these two, but you add them together to get that. Okay, so with this, you would not only inherit all these, and you'd inherit this one, but you'd get this linear combination of those two. Okay, you'd add them. And hopefully you guys know how to add things by now, just kind of in your head. Remember that thing, filling out fact things. Like you could say, okay, well, we have a red line going up here in the box that intersects this, that makes a disk. Okay, and then we have another red one that makes another disk. And that eventually fills out the plane. And now you've got these two planes added together, and you get more planes. And you know, you could add this translation to this and make you know, this translation would make a bunch of parallel red lines to that one. So you can just grab any two of these and just keep adding them together, and you'd see it would fill out a bunch of intersecting red planes and disks that are already shown here that are perpendicular to these, you know, the wires, or this axis here. So if you're not good at adding freedom spaces, one, get good at it. It's the most useful skill in this class. You know, if I give you a bunch of different red and black, you know, lines and arrows, and had you add them together, hopefully you can use it. Remember that chart I gave you with like 7 different cases on it? And I said if you just memorize this, you can fill in freedom spaces. That's what we're doing. We're just filling in this freedom space by taking that and that. We know the final one has those, but you linearly combine them and you get that. Okay? Okay, well, let's look at the constraint space of this guy. Okay, which is, you know, let's go back here. So check it out. If you have just a single red line, its constraint space is a bunch of intersecting blue planes, but there's also some black and orange in there. There's a black disk of pure moments, and there's a bunch of orange stuff in there that I didn't draw. Okay, and then the constraint space of this is a bunch of blue parallel lines and a pure moment there. So you could ask yourself, what's the intersection of these constraint spaces? The constraint space of this parallel module, the constraint space of this parallel module. Well, my goodness, you know, the only blue lines they share on these intersecting planes, and this one plane with these parallel blue lines, is a single blue line there. And this moment is very different than all those moments. And so all the moments go away. And you'd find all the orange lines of both go away as well. They don't share anything in common. And sure enough, what's common between these two is the constraint space of the system. This acts as if it's a single wire. Okay, and so you can see the freedom space of this wire is this, which is that, with all the screws here. Okay, so we just whether you realize it or not, I just proved something very interesting. Okay, so which is constraints in parallel, you linearly combine them. Okay, the freedom spaces of constraints in parallel, you find the intersection of what's common. Okay? Whereas when things are in series, when constraints are in series, you do the opposite. You find the linear combination of their freedom space, or you take what's common between the constraint space. Okay? So, yeah, so again, constraints in parallel, you add them. Constraints in series, you find their intersection. Okay? Freedom spaces in parallel, you find their intersection. Freedom spaces in series, you add them. You linearly combine them. So it's the exact opposite. And it's also interesting to note that there's an analogy with freedom spaces and compliance matrices, or compliance, and stiffness matrices and constraints. Okay, so like, remember when we made our stiffness matrices or even the scalar stiffnesses, I said springs in parallel, you add their stiffness. Well, stiffness is like, it's stiff, it's constrained. Constraints in parallel, you add them, you linearly combine them. Okay, but remember I said springs in series, what you do is you take their compliance and you add their compliance in series, when they're in series, and you get the compliance, the effective compliance of the whole system. Well, it's very similar here. Compliance is analogous to freedom spaces because those are, compliance is the directions that aren't constrained, that they can compliantly move. Freedom spaces are the directions that aren't constrained, they can move with compliance. And you add, just like you add compliance in series, you add freedom spaces in series. Okay? So you add constraints in parallel and you add freedom spaces in series. You add stiffness in parallel, you add compliance in series. Okay, so there's some really neat analogs mathematically to freedom spaces with compliance and stiffness matrices and constraints. Okay, all right, so that if you internalize these two slides, you kind of know the entire course in many ways and how to analyze and design these systems. Okay, if you don't understand these slides, we're going to do a ton of example practice and stuff. But let me just break down systematically now. Now that you know these principles, how you design a serial system. Okay. You might recall from one of the past lectures, we used FACT to design a parallel micromirror array where each mirror tips and tilts. In other words, gets a disk freedom space. So two intersecting rotations linearly combine to get a disk freedom space, right? And we went through all the subconstraint spaces and designed parallel systems, all the different parallel systems that can get tip and tilt, right? Well, now we're going to design a serial system. Okay, what you do, and it's really not difficult, all you need to know is, remember, if you have multiple parallel systems stacked in series, you basically add the freedom spaces of each of them to get the full freedom space. So if you know that, then you can say, okay, this freedom space consists of, let's break this into two different freedom spaces, just two rotations. And let's get one parallel module to achieve this rotation, and the other parallel module to achieve that rotation. And then when we stack them together, we'll get this freedom space. Okay, so what you do is you take a freedom space. That's the whole thought, the realization that freedom spaces add in series. So what you do is you take a freedom space, you break it into sub-freedom spaces, in this case the two lines. You take one of those sub-freedom spaces, and then you find its constraint space from the chart. Okay, again, this chart doesn't have orange or black. It's just to, this is the constraint space to design a parallel module. Okay, there it is. It's intersecting blue planes. So you would now draw that constraint space appropriately, orient it, align it with the freedom space, and use it to design a parallel system, parallel module that achieves that rotation. And you can see that if you have these two parallel blades that lie on these parallel planes, that they will get a rotation. Okay? Okay, and that, by the way, is over-constrained already, right? Remember, 6 minus 1 degree of freedom is 5. We'd expect to pick 5 from here. Each of these blades contains 3. they're an order of constraint of 3, so 3 plus 3 is 6, but so it's over-constrained by 1. That parallel module is over-constrained by 1. That's just a little review. Okay, but anyway, we've used one sub-freedom space to, intermediate freedom space. Sorry, I've been calling them sub-freedom space. Let's call them intermediate freedom space. Okay, you take them. Let's just go back here. You take the main freedom space, break it into intermediate freedom spaces, find their constraint spaces, synthesize their intermediate freedom spaces parallel module using things from the parallel pyramid, okay, and then take the other intermediate freedom space, okay, find its constraint space is the same one, and design its intermediate or its parallel subsystem, okay. Okay, so if we hold this one fixed, this will move with that rotation. If we hold this one fixed, this will move with the other rotation, this one. And so because they're together, if you just hold this one fixed, you allow the intermediate stage to just be free, and you grab this top stage will inherit that rotation, and the linear combination of all of them. And you can see there, here's the rotation of the bottom one, here's the rotation of the top one, and if you could, with just as much, essentially just as much compliance, if these were ideal constraints, everything would be infinitely stiff, and you could achieve all the except you could achieve all the rotations in that disk with infinite compliance. So these would be go motions, and everything else would be no-go motions if these were ideal constraints. Okay. So serial systems, there's many more serial systems than parallel systems that you can design, as you can imagine. So where there was a fairly limited number of different ways you could make your tip-tilt mirrors with parallel, there are many, many ways you can do serial things. And the neat thing about serial tip-tilt systems is you can shape the intermediate stage, you can compress it. This is like stacked in series, but if you make this interesting rigid shape, which you can make anything you want, you can kind of make them more compact and press them together to get the two rotations you want. Okay, so you can get interesting with that. Okay, so now we're talking serial systems, which means now things are allowed to be under constraint. Okay, and by the way, going back to this, this is a serial system. Obviously, it's stacked in series. Is this system here under constrained? Okay, let's just do a quick review. You could ask yourself, well, are there redundant degrees of freedom? Well, this one gets that one, and this one gets that one, and even though they're both rotations, they're not the same rotation. They're at different orientations and locations, except where they intersect, right? But the point is they're different things. So that means there's no redundant degree of freedom. That means it's not under constrained, and it also means if I hold this stage fixed with respect to that this would be very locked up, which it is, right? Okay, so again, we've and by the way, so this system is not under constrained, but it is over constrained, because remember I told you if this parallel module is over constrained and that parallel module is over constrained by 1. But if you ever take a serial system and you want to know if it's over-constrained, what you do is you ask yourself do any of the parallel systems in it, or any of them over-constrained? If even one of them is over-constrained, the whole system's over-constrained. It's kind of like a glass of water. If you put a little bit of dirt in it, the whole glass is dirty, right? So that's how you the rigorous definition of over-constrained. If any parallel module, one or more, are over-constrained, in this case, both are over-constrained. The whole system's over-constrained, right? Both would have to be exactly constrained for the system to be exactly constrained if it's a serial system. And remember, exact and over-constraint have nothing to do with under-constraint. Okay? This system happens to not be under-constrained, but it is over-constrained. Okay? All right. Okay, but let's look at under constraint here now. But last time we looked at under constraint, we didn't know what freedom spaces were. So now we're going to take a look at this. Okay, so remember this guy. I wish I had drawn its stage thicker and more rigid, and I wish I had drawn this thinner and more blade-like, but I didn't. But this is a parallel system with a single connecting two rigid bodies with a single blade, And you can see it achieves a translation and 2 rotations. That rotation, okay, and that rotation. Okay, very good. All right. If we stack it now in series with itself, turn 90 degrees, remember we inherit all the degrees of freedom of the past system as well as the introduction of the new degrees of freedom, and we get the linear combination of all of them. So for this, we would expect, there's 1 translation, 2 rotations. If we stack it in series, you'd expect 6 things. Okay, but we don't. We get 1 translation from there, 1 translation from there, 1 rotation from there, 1 rotation from there, and 1 rotation from there, which is in common between both. That's why you don't have 6, because there's a redundant degree of freedom. Okay, so you have 2 translations and 3 rotations. Okay, and I'm just doing a review here. We're not talking freedom space. Okay, and remember, because they both share the same common degree of freedom, there's a redundant degree of freedom, which means the top stage can rotate twice as far as it could otherwise. And it means that if you hold this fixed with respect to the ground, this guy is going to move. Okay, and so redundant degrees of freedom have much greater range. You can get to twice the range or more, right? Depending on how you design it. Well, you get the range of both of them added together is what you get, right? But it's worse dynamics because it's under constraint. There's a redundant degree of freedom. You're usually only measuring and driving the stage, and so you have the intermediate bodies that are not constrained and can vibrate around with that redundant degree of freedom uncontrolled. Okay, and that's bad. And you certainly wouldn't want to buy more actuators and sensors to control that too, because that gets very expensive. So, and it would be stupid. Just don't do that. Okay, unless you really need huge range. Okay. All right. So, okay, so that's that. But you might have said, well, this is stupid. Like, we said this rotation, but can it also rotate there? Can it also rotate there? And why draw the rotation at that particular axis? There's not a clean axis there. Well, the story is much cleaner when we look at freedom and constraint spaces. Like back in the past, that might have disturbed you when we did this. When we looked at this example. But now we can look at the constraint space of this is every blue line on this plane, the plane of the blade, and its freedom space. So you can look at here. That's the blue plane. Its freedom space is a plane with the translation arrow. It's this is a plane of red rotation lines and translation arrow. Okay, and so that means this stage can translate in a direction perpendicular to it, and the translation location doesn't matter. You can put it anywhere. And then it can rotate around not only this line, but every line on that plane, and this line, every line on that plane. Okay, so this is, the freedom space shows you the complete picture of all the ways that stage could move for that single module. Okay? It's not just those 3 random ones I kind of picked that were disturbing. You can do a bunch more, right? Okay, so what you should really look at is those are all the motions that parallel module can achieve. When we stack it on top of itself, those are all the motions that parallel module can achieve. If I ground this body and move that, those are all of its motions. And so the question is, if I ground this, allow the intermediate stage to be free, what freedom space does the stage possess? Well, just like this, it inherits not only those 2, but all the combination. Well, that stage is going to inherit all the rotations on this plane and the translation, all the rotations on this page and the translation, and the linear combination of them. Which, if you know how to linearly combine them, which hopefully you're getting good at from that chart, you could say, yeah. Anyway, you would find that it's a freedom space of a bunch of intersecting red rotations and perpendicular translations. Okay, and so that's the full picture of the freedom space of this final stage. If this guy's grounded, and that's the intermediate stage. That's what it can do. Okay. This stage moves with that one. If you ground this one, that stage with respect to the ground moves with that one. But together, if you allow this free to move, the freedom space of the top stage is all this. Okay? Okay, and you can see those original 5 things we picked did indeed lie within there, right? This rotation line on that plane, this rotation line on that plane, this rotation line at the intersection, and these 2 translations were in the disk. Okay? And you can see the whole freedom space of this, and by the way, there's a ton of screws in there too. Right, but it's analogous, or its constraint space is a blue line. Okay, so Okay, so here's the interesting thing. So by the way, that this guy is like kinematically equivalent to a wire, which is I'm going to talk about in a second, because it has the same freedom space as a wire, just a single blue line. Okay, but here's the important point when it comes to under constraint, because that's the point of this section here. The two intermediate freedom spaces was this guy, right? And this guy has 3 degrees of freedom in it. This guy, the final freedom space of the stage, had 5 degrees of freedom. So check it out. This intermediate freedom space, the freedom space of this stage, if this is ground, was 3 degrees of freedom. The freedom space of that stage, if this is ground, was this thing, okay, which also is 3 degrees of freedom. And then the final degree of freedom of the stage was 5 degrees of freedom. It looked like that freedom space. Okay, so already if we count degrees of freedom, we can see 3 plus 3 is greater than 5. So that tells you that it's under constraint. Okay, so that's what you do. If the number of degrees of freedom in each intermediate freedom space add together to be greater than the number of degrees of freedom in the freedom space of the final stage, it will be under constraint guaranteed. Okay? If they equal, though, if this was like 3 plus 2 equals 5, or this was 3 plus 3 equals 6, if they equaled, then it would not be under constraint. Okay? If it ever is greater than, then you've done something wrong and you've screwed up, right? There's no way you can add 2 intermediate freedom spaces and get a freedom space that's greater than the sum of their it's like 3 plus 3, it can't be 7 or something, or 3 plus 2 can't be 6, right? So you've done something wrong. Like if you ever get greater then you've got some problems, right? Okay. But this is a very valuable insight to identify whether something that's serial system is under constraint or not under constraint. Okay? Okay, and so, but going back, just remember, I said, note that the freedom space of that stacked blades that turn 90 degrees is basically a wire. So this is kinematically equivalent to a wire. They have the exact same freedom space. And so, cool thing about kinematic equivalence is you can just, if you know this basically has the same degrees of freedom as a wire, you can, swap it out. So remember we designed this guy that got, it's 3 intersecting rotations and everything in a previous fact lecture here. You might think, well, that's all the ways you can get that motion with the compliant mechanism. But if you remember that, by stacking these, you can get something that's kinematically equivalent, then you can just swap it out. And it'll get the same degrees of freedom. And notice we put 2 of these in series. No matter how many you put in series with it, it doesn't change the freedom space. You can prove that. And so what we did is we just took wires and swapped it out for these guys. And what it does is, even though it's kinematically equivalent, meaning it achieves the same degrees of freedom, it has very different everything else. It has a much higher load capacity before it buckles. It'll be much stiffer. There's natural hard stops, so it won't yield. There's resonant frequencies are different. The elastomechanics, the stiffnesses are very different, but they get the same degrees of freedom. So if you ever, this is the whole concept of kinematic equivalence is very valuable. We'll talk about it in a later lecture, which is, most of the things you design with FACT, you design with a bunch of wires, but sometimes wires are tough to fabricate, or you don't want to make them, or they're flimsy or something. So if you have a big library of kinematically equivalent things, you can just swap them out. You design it with wires and swap them out for stuff like this, and you can be even more creative in your designs, right? Okay, but we'll come back to kinematic equivalence in a later thing, okay? Okay, okay, so let's look at flexure coupling. So I'm going to do a case study. So I've kind of taught you the principles to use FACT to design serial systems, but now we're going to do some practical case studies and give you a few more insights, okay? And this case study is, let's design a flexure that is a flexure coupling. So you might remember, I mentioned this in a past lecture, if you get a motor that's, this rigid motor, and you want to attach it to a rigid shaft to drive something, if you directly connect it and bolt it down and everything, the chance that you perfectly aligned it is 0, and when you turn on the motor, you will transversely load and harm that motor, and it'll break itself very quickly. So what people figure out is, you know, by the time we mount all these things, get it as close as you can, and then get this like this rigid component with these two slots cut in it, slide the slot in the shaft of these two things, and just kind of put it on loosely, and this will very rigidly pass the moment through, so it can the motor can still drive it, but it'll accommodate all the